Today, we will be talking about the factors that affect the rate of reactions. There are four original factors that could affect the rate of a reaction, namely, nature of the reactants, concentration of the reactants, temperature, the presence of a catalyst. But we will only be talking about the three of them, all except the first one. The rate of a reaction at a constant temperature varies with changing concentration. This could be denoted by the rate law expression, often called the rate law. Rate is equal to k times a raised to x times b raised to y, where k is the specific rate constant. A and b are the concentrations in molar, and x and y are the orders of the reaction. So let's have an example. The value of both the concentrations of A and B is equal to 2, and the values of x and y are 1. And applying the rate law, we get this expression. And solving this, we'd wind up with 4k. This is the value of the rate of the reaction in terms of k. So let's have another example. Let's change up the values of the concentrations of A and B to 3. We'd get this equation, and we'd wind up with 9k. Remember that from our first example, we got an answer of 4k. Now that we've increased the concentration to 3, we got an answer of 9k, which is far greater than 4k. From here, we can say that the higher the concentrations, the higher the rate. So rate and concentration are directly proportional. When the concentration is higher, the chances of particles colliding with each other is also higher. This leads to an increase in the rate of the reaction. Moving on to temperature. The temperature, simply put, will indirectly affect the rate of the reaction by affecting the specific rate constant. This is seen through the equation K is equal to AE raised to negative EA over RT, which is also called the Arrhenius equation. A is the frequency factor, E is a constant which can be found in your calculator, T is the temperature in Kelvin, R is the ideal gas constant, and EA is the activation energy. When the temperature is increased, EA over RT is decreased since the denominator has been increased. Thus, the inverse of EA over RT is increased. K is then increased because K is equal to AE raised to negative EA over RT, and the reaction is sped up. Lowering the activation energy has an effect on the specific rate constant. The effect of a catalyst on a system can also be shown through the Arrhenius equation. When a catalyst is added onto a system, the activation energy decreases, so EA over RT decreases, and negative EA over RT increases. So, E raised to negative EA over RT also increases, which makes K increase and the reaction speed up.
These bitches want Nike. They looking for a check. Tell them it ain't likely. Say she need a ring like Carmelo. You must be on that white like Othello. like me. I don't play, I don't make time. But if you need dick, I got you. And I am from the line. Go up for ASAP. R.I.P.